and then we will get started. I need to open up one more thing, actually. When we get to vision. As I'm opening up the PowerPoint today, I have realized that I did not post that yet. That is my bad. So I will try to remember to do that today, after class. Okay, hopefully it's gonna focus in for us. Very few administrative details today. I told you that we were going to talk about how to sign up for your final exam, and we are, very briefly. It's pretty straightforward, I hope. There is a link on Canvas, and I'm going to walk you through that in just a minute. There's a link on Canvas that allows you to sign up for that final. I've also put a video instruction on there. I appreciate that. I was helping, working at my sister's, so I'm in her toy room, so please ignore all the mess behind me. But the video instructions kind of walk you through not only how you sign up, but why you might want to sign up. So I'm not going to go over that level of detail today, but I do want to make sure that you see exactly where you go to sign up. You are responsible for keeping track of your grades, right? We talked about that after each assessment. The grade sheet that I posted for you after the first assessment was updated, of course, after the second assessment, and has now been updated after the third assessment. I would recommend, and I say this on the video also, I would recommend what you do is download a new grade record and then copy the grades from your old record for assessment 1 and 2 into the new one. And the reason for that is the new record does automatically calculate your current content grade for you. If you, however, just copy and paste assessment 3's record into your old record, it's not going to do that. So it's better to go that other direction. Obviously, you can do it yourself for if you are comfortable with equations in Excel, of course. So I would encourage you to do that. I've also put the 12 elements for optics. Now we should get through all 12. So I'm pretty hopeful that we will get through all 12 elements for your optics exam next week. So what you can do then is you can do a little playing with how many M's do I need to get, how many P's do I need to get, how many, so on and so forth in that optics exam to get the grade that you're hoping for in the class, if that will help you facilitate what you should sign up for the final. The content elements, so for every assessment, there was a list of content that is posted in Canvas. Please be aware that that is not connected to anything in your book. There are certainly readings in the book that identify where you can find those content pieces in the book, but those are just our listing of essentially how we went through the material. Every test, assessment 1 was for unit 1, assessment 2 was for unit 2, and assessment 3 had units 3, 4, and 5 all together. Every category grouping unit has its own list of content, and that is posted in Canvas. It's the very first thing under each unit. So that's what you should be looking at to know not only what you're going to be tested on each unit, but what you might want to retake. There are a couple of things I do want you to be aware of. For the final exam, there will only be one question per content. So you may recall during all of our assessments, there were 2 questions per content. So when you got your grade sheet back, you saw 2 grades, and then it was formed into a single grade. That single grade is your record for that content. So this last exam, unit 3, concept 1 had 2 questions, and you were given 1 grade for that concept in unit 3, concept 1. If you sign up for a concept for the final exam, there will only be 1 question. It's not a doubling like I do during the assessment period. And so it's sort of a one-shot deal. There is a risk to taking this final exam. I think it's a risk worth taking, but there is a risk worth taking to take. And so make sure as you're signing up for the final exam that you are comfortable with the content you're signing up for. I will replace your grade. Okay, so if you sign up for something that you have a satisfactory grade on and you don't do well on it, you're going to end up with that not doing well. And that philosophy is really, you should at least be able to perform as well as you did during the term. So that's the risky part of the final exam and the way that I do it. Now, if you have, and I've said this multiple times, so hopefully it's sunk in, if you have a E or an L, so lack of evidence or an emerging grade, those are failing grades on a content. You can't do worse. So if you have any E, emerging or lack of evidence grades, I would encourage you to, at the very minimum, sign up for those on the final, because even if you didn't even take the final, you'd still not change your grade. I am more than happy, and I've already had some students set up appointments with me to go over your grade record and give you some advice on what you might want to consider signing up for on the final. It is really important that you do this correctly. So watch that video, and obviously now pay attention when I go through that process, because if you sign up for the wrong question, you're going to get that question and it's going to replace your grade. So if you accidentally sign up for a question that you've already mastered and you run out of time or whatever, you mess it up, who knows, that's going to change your grade. So it's really important that you sign up for what you intend to redo on the assessment. Okay. It's not a difficult sign up process, but I want you to be very attentive to what you're doing. So how do we do it? All right, I'm going to share my screen with you. First, I have to log into Canvas, as it logged me out right before I came here. And hopefully it automatically, nope, of course not. It's going to ask for my double verification thing, or dual mobile, or whatever it's called. All right. So let me share this now with you, and I got to put it in student view before I do that. All right, we should be good. Okay, share. I do not understand why this does not share for me. Well, that's no good. Let's try this again. Well, let me see if I can just share my screen, and you're all gonna like zoom in, and then I'll just open this up. Okay, I need somebody to tell me in the chat that you are seeing our Canvas page, or unmute and just say yes.
No.
You're not. Okay, thank you. So let's try that again. How about now?
Yes.
Perfect. Thank you, whoever unmuted. Okay, so here is our Canvas page. This should be in your view. Right, the very first module is going to be your final exam sign-up link. Now, the instructions in this module, this is the video I made yesterday. So if you click on that, you can feel free to rewatch that video. All right, so go back home. That just tells you how to sign up, gives you some suggestions. This link is a really straightforward link, but I want you to pay attention. This is super important. Set an alarm, set a notification, write it on your forehead, whatever you need to do. You have to sign up for this by midnight on December 11th. Well, actually midnight on the 12th. So 11:59 p.m. on December 11th. That's next week, Friday. Do not miss this deadline. Do not. You will not have the opportunity to take the final exam if you miss this deadline. These take me a long time. So I start on that Saturday, and it's a miserable Saturday for me, but do not miss this deadline. All right, so all you do is click on the link, and it's a Google Sheet. Make sure you put your name in, first and last name, please. And then each question in this Google Sheet corresponds to one of our tests. So this is the first test, test 1, unit 1. It was on Introduction to Motion. Every concept, and your test was in order of concepts, so that should be pretty straightforward. All of unit 1 is in the same test, concepts are in order, and then here's the description of those concepts. This list matches the list in Canvas. And you simply just check which one of these you want to reassess on. So it's just a checkbox. So click every concept you want to show up on your own final exam. Unit 2 was its own test as well. So again, every question in this test is from Unit 2. All of the concepts are on the Unit 2 concept list. Same thing, maybe you have a couple more, who cares, right? So check what you want to reassess on. The one to pay the most attention to is this last assessment, because there are 3 units in that assessment, 3, 4, and 5. So unit 3's concepts, like your exam, were first, and they are all listed. And then you see that there's a unit change and then 2 units for concept 5. So I just want to make sure you are signing up for what you intend to sign up for. Make sure you do that, okay? You have a spot if you have any questions or comments or concerns, that sort of thing. And then you just hit submit and it will submit. Oh, it's going to make me put in a name. So Dr. Hopp. All right. And then you just hit submit. Okay. Then your response has been recorded. All right. Remember, next week, Friday by midnight. Friday, 11:59 p.m. Saturday by midnight. Okay, question. You can pick them across. Absolutely, no. So you can pick as many assessment questions as you want across any of those first 3 exams. So select in each one, does not have to be on a single exam. Good question. Couple of things to be aware of. 1, you get 2 hours for your final exam. I always give you that half-hour technical buffer, but your final exam will be 2 hours and 30 minutes for your technical buffer uploads. So you have to be aware of how many questions you sign up for because of that time limit. If you leave a question blank, it becomes an L. So do not just sign up for everything and hope that whatever you don't get to, I'll just keep whatever grade you had. This is your responsibility, and there is a risk to it, a level of, okay, what do I really want to show Dr. Hopp that I can do? And that's what I want you to take ownership of. There is not, Ian asked if there's a minimum for topics. There is not. It is entirely up to you. So if you did not real great on that first exam and your entire final is that first exam, fine. So this is all your opportunity. Okay, great. So Ben's asking about I think, Ben, what you mean is assessment 4. So unit 6, this optics, this last one. So Ben is asking about, will this final assessment we have look like the rest? The unit 6 assessment or optics assessment. And the answer to that is yes. So there will be 2 questions per concepts for optics, just like everything else. And Ben, thank you for bringing that question up, because be aware that this is a one-shot test, right? So you will not have your optics exam to sign up for, obviously, for the final exam, since the optics exam is after the sign-up period. You also will not likely get your scores back on that 4th exam prior to you taking the final exam. So that is just something to be aware of. It will affect your grade. There are 12 concepts, so you have to sort of gauge how comfortable you are with those. The optics exam will open, Kyle's asking when it is. As a reminder, that exam will open on Monday, not this coming Monday, but the last day of class. So we do have a class on Monday.
the 11th, 12th, 14th. Classes end on the 15th. So your optics exam opens on Monday. Your final exam opens on Wednesday. So the scheduled day for our final is when you will take the final. So it's a short turnaround time between your optics test and your final exam. Any other questions? Will the questions on the final be short answer, multiple choice, or it depends on the concept? It depends on the concept. So they are typically short answer. I typically do not have a multiple choice question on the final. That's a good question. However, there could be what's a multiple choice question that you answer and then have to justify your answer. That has shown up on the final exam. So you choose one of the choices and then you have to say why you chose it, for example. Most of them, however, will be short answer. And then if there are any that are problem solving, of course, you'll have that problem solving option. So Nick asked, the final is optional as a redemption. That is correct. So Nick, you do not have to take the final. So if you are happy with your grade and you are comfortable with how you think you will perform on the final assessment, the fourth assessment, optics, the final exam is purely optional. So, and if there have been times that will not happen this time because the turnaround time is way faster, although maybe, who knows. I have had the occasion that sometimes I will just hammer down and grade your fourth exam. Usually I have more than 2 days. And then tell you what your final grade is and I'll provide you the option to opt out of the final you signed up for. The beauty of that is I have less to grade. So there is a motivation for me to do that. Sadly, given our time structure for this particular semester, I don't think that will happen. But if I am able to calculate your final grades for you before you physically take the final, I will provide you that opt-out option. That being said, if you have a solid A in the class right now and you're feeling good about optics, there's no reason for you to take the final, then don't take it. It's entirely optional. Long answer to a simple yes or no question. Anything else? I want you to feel comfortable about this, and I really want you to reflect on what to take so that you can be successful and show me what you know. If you know stuff, I want to know you know it. Anything else? Let's take a drink, let people formulate questions if they have them, and then we'll move on. Okay, awesome. Please reach out to me. I am happy to set up a Teams meeting. We can go over your grade. I don't like to do that so much over email, and I won't. I'll just say it's easier for me to talk to you, so just be warned of that unless it's a quick question. All right, so we ended on Monday talking about an introduction to lenses and specifically the convex lens and how lenses affect light. And that was all just those principles of refraction. And so today we're going to review that real quick, and then we are going to make sure we have the vocabulary because that's going to be important. We're going to move into image formation and what that really means and how that looks. So the type of lens that we started looking at was this convex lens. So this football shape lens, and it had the operational definition of a converging lens, and that was because of its ability to take rays of light and refract them going into the lens and refract them going out of the lens in essentially the same direction. And so they converge, parallel rays of light converge to a common point. So we'll just recap that. We see, and I think you'll be able to see this much better in here. So we see these parallel rays of light, and they're all being converged to this very common location. They all intersect at that common location. Now, it's not just parallel rays of light that converge. As we look at image formation, we'll see that this converging behavior is what produces the images that we are going to talk about in terms of lenses. Before we do that, let's just go through the vocabulary and make sure that we are comfortable with using this language as we move through image formation properties. Okay. So let's get rid of that. So here is our lens representation, and we're just going to use a single line to represent our lens. This is, in our case, a convex lens. If we bisect that lens perfectly perpendicular, this is what we refer to as the optical axis. Okay, and I'm going to use my lens here that we were using before to give us a gauge of that convergence point. This might be more difficult to see with the lights on, but all of the light rays are converging at this point that I've drawn here. This is what we call the focal point. And the distance between the lens and that focal point is the focal length. So we talked about those vocabulary previously. Now, we're going to add a couple new terms. But before we do that, I want you guys to make a prediction. We said that the shape that the lens is refracting this light, right? We went through the actual refraction and did the ray diagramming with that refraction to cause these rays of light at the top to be bent down and the rays of light coming in at the bottom to be bent up. Now, thinking about refraction and what influenced the amount of refraction that we saw, what happens if I change the shape of the lens? I am not changing the material of the lens. This lens and the one on the board are identical in material. Do you see this lens is a little curvier, okay? So if I change the shape, if I make a lens more curvy, does anything change about how that lens influences rays of light? Now, first, what could possibly change? Well, the only property of the lens that we've really identified here, the rays of light are independent of the lens, they're coming from this laser ray box, is where the lens causes those rays to come together, the focal point. So the gist of the question is, does changing the shape of the lens affect the focal point? And if so, how? So I'm going to put up options for you, and I want you to do that voting like we do with your little emoji. So mark what you like. So, well, the question is, does a curvier lens increase the focal point, decrease the focal point, or does it remain the same? And by increase, I mean it'll move the focal point further away. Increase the focal length would have been a better way to say that. Decrease the focal length, or does the focal length remain the same if I put in a curvier lens? So I want you to sum in my chat. I've given you increase, decrease, or remains the same. Tell me what you think will happen with a curvier lens. Will I increase, decrease, or remain the same? All right, so I'm getting some good voting in. I'm going to check how many people I have in the chat, in the class today. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 of you. So I should have 12 votes. All right, 6, 7. I only have 7 votes. So you're totally risk-free on this voting idea. Okay, and we're split. I like when we're split a little bit. So let's test this and then let's talk about it. All right, so I'm going to take, and hopefully you can see that this lens is curvier than this lens. All right, so let's turn the lights off. This was our original lens. And as I place the more curvy lens in, what do we notice? We notice that our focal point gets closer to the lens. I have decreased my focal length. Let's turn the lights back on and talk a little bit about why that might be. So we're going to decrease the focal length as I make a lens more curvy. Remember when we looked at the lens itself and how light refracted through it when we blew up sort of a portion of it, remember? And if I take that parallel ray of light and I bring it in, so there's my parallel ray of light, just because it's an easy one for me to draw. Talked about that too. The refraction is relative to the normal. The refraction is relative to the normal, that angle of refraction. That's a very, very important concept to keep straight. So if we draw our normal on this image, we know that that refraction from low to high is towards the normal. This is the no refraction case. We're going to move towards the normal, and that gives us that downward bend. And we, of course, did it on the exiting time too, so you can review that if you need to. Now, what happens if I make the lens more curvy? If I take this curve and I make it sharper? Well, as I do that, what does the normal force do? It starts to tilt relative to the original. And if the normal force starts to tilt, going towards that normal also has to tilt in a way. Think of it as also tilting. And so those rays of light are coming down at a steeper angle, all relative to the normal. And as I tilt that normal force, my angle of incidence changes slightly, and therefore my angle of refraction has to change. And I get a sharper downward deflection of those incoming rays. So, because what I'm changing is the angle of incidence by changing that normal. All right, we said that the angle of incidence was one of the two things that affected how much a light ray was refracted. So if I increase that angle of incidence, I have to increase the angle of refraction, and I get a sharper downward angle. Conversely, if I decrease it, if I take a lens that is less curvy, so here's my original. There's my original. And I have a less curvy lens. The opposite should happen. I should increase the focal length. So less refraction is occurring. When the less refraction occurs, the time, the length it takes to get those rays to come together is longer, and I increase the focal length. All right. So shape of the lens plays an important role in our refraction because it affects the angle of incidence. The other thing we said was important in how much refraction occurs was the difference between the two mediums. That was critical, the difference between the two mediums. I can't make a change of that, unfortunately, on the board because I'm in this medium of air. But what do we think would happen to the focal length if I changed the external environment? Let's say I take my system and I put it in water. So the light is in the water. It's very important. The light is in the water and the lens is in the water. So my parallel rays of light are within the water, going through a lens in the water, and I'm going to look at that focal point in the water. So I want you to answer the same question. Do I increase the focal length, decrease the focal length, or does it remain the same because I'm not changing the shape of the lens? I'm only changing the medium with which the lens is in. So what do we think? Increase, does my focal length get further apart? Decrease, does it get closer to the lens or does it remain the same? Again, we're putting it into water. We're putting the system into water. What do we think? All right, we're getting a split again. Okay, a little bit more votes on the decrease of focal length. Okay, let's talk about this. So when we talked about refraction, we said that the closer the two indices of refraction were, so the closer the optical densities, the less refraction occurred. So it was the two mediums, that boundary, remember, that we talked about. When we had a boundary between air and water, versus a boundary between, sorry, not between air and plexiglass was the example we used, versus a boundary between water and plexiglass. And I want you to think about the football field again. So when we're really on firm ground, going to really sticky ground, we get a big change. So that would be the unrefracted ray. We're going from low to high, and I'm going to see a change in my ray. Now imagine going from a sloppy field, lots of external play in this particular football game, not as much as in the middle, but a lot of wide things happening. So it's a little mushy to more mushy. So not firm to mushy, but a little mushy to mushy. You're going to be influenced less by that. So water is closer in its optical density than plexiglass. So if given the same angle of incidence, I'm going to get less refraction going from water to plexiglass than I am going from air to plexiglass. Again, thinking about that, you slow down going from muck to more muck, but you really slow down going from firm to muck. Well, if I take my lens and I put it into water, then I am changing the difference between those two mediums. And I'm making that difference less. So as that ray of light comes into the lens, it's now going between water and the lens versus air and the lens. And I will get less refraction in that case because the difference in mediums is less. Therefore, less refraction is going to cause it to take a further distance for those rays of light to come together. So as I decrease the difference in mediums, and that's the optical density, the index of refraction, those two words, I will increase the focal length. I will increase the focal length because I get less refraction. Less refraction takes longer to come together. So increasing the curvature decreases the focal length. Decreasing the difference increases the focal length. And it all fundamentally comes down to the idea of those basic principles of refraction. So to focus on what ultimately is going to be how do we affect images by these two ideas, changing the shape of the lens or changing the medium, we can rely on those ideas of refraction. So those you want to get yourself solid on. What are the principles of refraction? Then how can I apply those principles to a lens situation? Okay. So let's move to image formation. I'm going to erase the board so we can kind of start fresh. Any questions, pop them up. And we'll look at this idea of image formation. All right. Okay. So when we look at image formation in a lens, we're going to have to identify some vocabulary, the same vocabulary we talked about just in looking at lens properties, but also a few more. So here I'm actually going to draw 3 optical axes above one another, and here are my lenses. So this is going to be the same lens in all 3 cases for our initial approach. Now, the lens, this lens and these 3 optical setups are in the same medium, and the shape of the lens is not changing. So both the medium and the shape of the lens influence where that focal point is located. And I'm just going to identify a focal point for this lens. So we're just going to keep the focal point the same in all three cases because the lens is the same and the medium is the same. Yeah, that's pretty good. I think this lens is a little off kilter. All right. Now, we're going to now look at how we form an image of an object in a lens situation on a screen. So whether that is a lens in a camera where we want to take a picture of something and that image is going to be burned on film, or in a photocopy machine where we want to make a copy of something and that image is going to be produced on a piece of paper, or our eyeball, where the image has got to be produced on the retina so our brain can interpret it. We're going to look at how that image is formed and what we need to do to make adjustments to make sure that image is crisp and clear and turns out perfectly. So the first thing we need to have is an object, all right? So I'm going to place my object on, that's what we're either taking a picture of or looking at, and place my object here on the left side of the lens. And I'm just going to use a very simple object. I'm just going to use an arrow. All right. Now, we're going to model this object as being something that produces its own light. The same would be true if it's an object that's reflecting light, like a tree or whatever that we're looking at. We don't need to worry about how the light's hitting it and bouncing off. We're just going to pretend it's coming from the light, the object itself. We know that means there are light rays coming from all directions and at any point along that object, in straight lines and in all directions. We're going to use that ray model like we've been using. Now, that means that the very tip of this arrow has rays of light coming out in all directions and in straight lines. And every one of those rays of light is representing the tip of the arrow. Think of it as it's carrying that information. It is the tip of the arrow. Similarly, rays of light are coming from the middle of the arrow in all directions. And those rays of light are representing the middle of the arrow and through the entire object. So like we modeled our long filament bulb as individual point sources of light, think of that as how we model any object, that every single location on that object is its own point source of light and is representing that location and that piece of the object. So this head of the arrow, this tip of the arrow, is a gazillion light rays shooting off of it, all representing the ray that's the tip of the arrow. One of those rays of light is parallel to the optical axis. There is a ray of light that comes from the tip of the arrow that goes parallel to the optical axis. And we just identified that rays of light that were parallel all converge at the focal point. We saw that in our demonstration. So this ray of light is going to go through, be refracted, and go through the focal point. This is what we call a principal ray. And we're going to look at 3 principal rays. This is the first one. All right. So parallel rays of light are refracted through the focal point. Now, let's imagine for a moment that I took my 5-ray razor ray box, right? And I put it on here on the left side of my lens. But what if I had put it on the right side of my lens? What would have happened? So here's my lens. And if I put it on the right side of the lens, well, those rays of light all converge to a common point, the focal point. So that has to tell me that on both sides of these lenses, this lens, there's a focal point. One on this side, one on that side. And if the lens is the same curviness and in the same medium, well, those 2 focal points have to be the same because it's about the curviness in the medium. So not only is there a focal point on the side of the lens that I was demonstrating the focal point on, but there's one on the other side too, and it's exactly equal in distance because, well, I don't know what side I shine the light through, and it shouldn't matter. So there's a near focal point, near being the one on the same side as the object. And there's a far focal point, one being on the opposite side of the object. So those of you who liked Sesame Street, Grover did his near, far, near. You can think of your focal points as the near and far of Grover. Okay, so if that's the case, that means that a ray of light coming from this side, parallel to the optical axis, should be refracted through the focal point on this side. So I could flip that around, and then I can say that a ray of light that is through in line with the near focal point should be refracted parallel, because the mediums are the same, and the angle of incidence and the angle of refraction then have to be proportionate to those mediums. So this is a second principal ray. It's a ray of light that I know must be refracted in a very specific way, given the lens shape and given the medium which it is in. So this ray of light also represents the top of the arrow. Also represents the top of the arrow, just like that parallel ray of light represented. And so I have somebody calling me, so I'm just going to ignore that. So it's not on our audio. So we have two rays of light, both representing the top of the arrow that we can draw. And there's one more. If the angle of incidence and the angle of refraction are both 90 degrees, the ray will remain unrefracted. And it's hard to visualize this, but this will happen for a ray of light that goes through the exact center of the lens. So a ray of light in line with the center of the lens, meaning the bifurcation of that lens with the optical axis, remains unrefracted. This is our third principal ray. It's a convenient one. We don't necessarily need to draw it. We only need the two. So if that one is less easy for you to visualize, don't worry about it. But it too represents, there's my arrow, pre-refraction. There's no refraction in this case. It's at 90 degrees. And it remains unrefracted. It too represents the top of the arrow. And what do we notice? All three of these rays of light are converging at the same location. And all three of those rays of light represent the top of the arrow. So the top of the arrow is reproduced at this location. And it turns out that every ray of light representing the top of the arrow, regardless of how it hits that lens, will be converged at this location. These are the ones that are easy to draw because I know exactly how they're refracted. But once I have them once I have them drawn, I know exactly how the rest of them are refracted because it has to go through the common point. So a ray of light that hits the lens at that location, which is some angle relative to the curvature of the lens, will be refracted through the focal point. Not the focal point, sorry, through the point of convergence. Because this is the location that all rays of light representing the same location on the arrow, in this case, the tip of the arrow, are converging. Okay. So if that's the case, if I were to put my film or my retina or a screen at this location, then I will get a reproduction of the tip of the arrow at that location. And similarly, the middle of the arrow, well, parallel ray of light through the focal point. Through the focal point, parallel ray of light, we'll find at the middle of the arrow, all of the rays of light converge at a location that will allow us to represent the middle of the arrow. And if I go through that entire arrow, we see that the entire arrow is reproduced at an identical location on the far side of the lens. So this is what is known as the image. So here is a couple more pieces of vocabulary. This is our image. It is what shows up on the screen or the film or the back of my retina. This is our object. It's what we are looking at or taking a picture of or photocopying. The distance between the object and the lens is the object distance, well named. The distance between the image and the lens, wait for it, the image distance. All right. So, a couple more bits of vocabulary. Now, what do we notice about this image and this object? Well, the object is a specific height. The height of the object. The image is also a specific height. We call that the height of the image. And we notice that they aren't necessarily the same. In this example, the object height is larger than the image height. So the object height, when I take a picture of it, is going to be different than the image. Well, that makes some sense. Imagine if you took a picture of your mom, and because we should all have pictures of our mothers, and you photograph it onto a piece of film, and the camera film, well, you guys don't even probably know what camera film is. The digital camera film, if you had a piece of film, it's just this big, and your mom's really big. So how do you get a little teeny picture of your mom? Well, the image, what gets burned on that film, has to be smaller than the object. Okay, so a couple more pieces of vocabulary to think about. Now, what happens if we change the location of the object? So we're not going to change the height difference. We're going to keep the same object. I'm going to move it farther away from the lens, and I'm going to move it closer to the lens. So before we do that, because we're going to follow the same process of ray diagramming and image formation in order to determine that answer, but I want to make sure there's no questions on any of this description so far. Okay, so let's move our object. Let's start with moving it closer. So I'm going to keep the object height, same arrow, just moving it closer. So the distance of the object decreases. Again, the distance of the object is the distance the object is from the lens. Okay, well, let's use our primary rays to give us a sense of where the image will be produced. So we said one of those primary rays that we want to think about is a parallel ray of light goes through the far focal point. A ray of light through the near focal point comes out parallel. I didn't draw my arrows long enough. All right. So those are our two primary rays of light. They're the easiest ones to draw, but we also have the one that goes through the center. It remains unrefracted. Okay, so where does that leave us in terms of our image? Well, all of these rays of light represent the top of the arrow. Everything representing the rest of the arrow will be reconstructed. What do we notice? Well, we notice two things, I hope. First, As the object distance decreased, our image distance increased. The image got further away. So if I wanted to take a picture of this object, I would need to move my screen further away from my lens. What else do we notice? The height of the image increases. So two things happen in image formation using these ray diagrams. We can see that. Well, what happens if I move my object further away from the lens? Using the same principal axes, parallel ray of light goes through the focal point. A ray of light that's in line with the near focal point comes out parallel. That's a horrible parallel. Holy buckets. Comes out parallel. And we see it wasn't a drastic change here. I didn't go that much further. Actually, not really very further at all. But we see that the image moves a little bit that way. So the image distance decreases when our object distance increases. And it's very hard to tell because I didn't make a drastic change, but our image height decreases. So to just verify that for you, I'm going to take this ray of light. My horizontal lines are not good today. There's that. Good grief. I'm going to take out this object and I'm just going to move it even further back. This ray of light doesn't change because a parallel ray is a parallel ray. But as I look at my ray of light through the near focal point, I really need a meter stick. You can see that even tinier image, which you probably can't see because it's too far away, but it moves closer to the lens. Is there a limit to this? Let's imagine that I move the object really, 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 really far away, like the sun. The sun's really far away. And as I do that, hopefully you can see that if we're going to compare this ray to this ray, to this ray, to this ray, these rays are getting shallower and shallower. The rays of light, we have our parallel one, and we have that one that's heading towards the near focal point, which is getting shallower and shallower and shallower, more and more parallel. And as I go further and further and further away, my image is getting smaller and smaller and closer to the focal point. Because remember, the focal point is where all parallel rays of light converged. So as I get more and more parallel, my rays of light are going to converge closer and closer to that focal point. And indeed, that's exactly what happens. So let's imagine that you're a cruel kid. I always get really nervous when I talk about this because I feel like people are going to get really mad at me. So I didn't like ants because my job as a kid, which sucked, was to sweep the ant hills on our patio. And our patio had these patio blocks like this that were put together. It was very lovely looking, but a lot of crap got in between them of sand and ants. I lived in a place that was a lot of ants, and I had ant hills all over, and I hated it. And it was my job. That was my childhood job. Yay, thanks, Mom and Dad. Fourth child, I guess, to sweep all the ant hills every frickin' day. These stupid ant hills would show up. I didn't like ants at all, and I'd stomp on them a lot. And then I learned physics. Well, I just loved physics. So I learned that if I took a lens like this one and I took the sun, it would converge those rays of light to a very specific spot, and the sun's energy is hot, and then I could get the ants by doing physics. So I'm not sure if my love of physics was positive or not at that time, but nevertheless, it allowed me to get rid of the ants in my patio. Now, a more practical way one might do that is, if you're stuck in the woods and you need to start a fire to keep yourself warm, and you happen to have a lens like this, which you might if your vision is bad, you could use it to start a fire too. Probably a more humane thing. All right, so image formation in a convex lens. Some important principles to keep in mind, but you can always revert. I would rather you not memorize this stuff, like, okay, if I decrease the object distance, I increase the object image distance, because I'd rather you be able to do the ray tracing to always confirm for yourself. Now, there is one more thing I want to identify for you that's important about this image, and that is, what do we notice about it relative to the object? We notice that it changed locations, and we notice that it changed its size, but we should also have noticed that it's upside down. So this is an inverted image. And those of you in photography, your film is upside down when you develop it. Yeah, it's easy to just flip it over. So this is our inverted image, and this is very important because it identifies something for us. I get to produce this image on a screen. It's what we call real, meaning that rays of light are truly recreating the object. These rays of light are representing the top of the arrow and truly recreating it. It's real. I can take a picture of it. I can put it on a screen. I can burn film. I can see it in my visual system. Real images are always notated by the fact that they are inverted. So an upside down image is real. And it's made by true rays of light. Now, you might be thinking, what else is there? And obviously there must be something else, or I wouldn't be emphasizing it, and we're gonna get to that. So, convex lens converges the light rays, brings them together to make a real image that we can put on a screen. So let's just look at that, physically look at that. And I'm gonna turn the camera, so if you get sick, you know the drill, close your eyes. All right, so I have an optical bench set up here, and I need to turn my screen so I can make sure we're seeing what I want you to be seeing. Okay, so here's the optical bench. I'm just gonna decrease the light a little bit, but not all the way. This time you'll be able to still see me. Okay, and what I have here in this optical bench is my object represented by this light box. So you can see this object. You cannot see this object. It's just a bright light in there. But you're going to trust me that this object is an arrow. Okay, so an arrow pointing up, and now it's crooked. Okay, an arrow that's pointing upright. It's actually a crosshairs, but we're just going to worry about the arrow pointing up. I have a lens. It is a convex lens, and I have a screen. Now the screen represents where that image is located relative to where the object is and the lens. So right now, how I have these positioned, you can see, hopefully this is gonna work. I don't know if it's in focus, but for you, sadly, but this image is in nice crisp focus, meaning that the top of the arrow in this object, all light rays representing the top of the arrow are converging at a common point here, and it's inverted, so in focus and inverted. So our first image formation plan that we looked at was, we said that if I move the object closer to the lens, I'm going to slide my object closer to the lens, my image will increase and it will move backwards, so further away, increase the image distance. So I am concerned you can't see this, but I didn't move the screen yet. And what I see on the screen right now is a blurry image. A blurry image. I've moved my object closer to the lens. You saw that. And I get a blurry image. I'm going to pause here for just a second. Rotate the camera back to the front board so don't get sick. Okay. And what I've done, what I've represented over in the demonstration is that this screen has not changed location. Okay. So I'm just going to put a mock screen there when I move my object closer. And we get a blurry image on that screen. Why? Why do we get a blurry image? Why do we see something blurry? Remember, each of these rays of light and everyone in between represents the top of the arrow. That means that the top of the arrow, information about the top of the arrow, is hitting the screen at multiple places. In fact, all through here is all the top. Well, that's confusing because the top of the arrow isn't in multiple places at once. It's in one spot. And so this object, this arrow, the top of the arrow specifically, is very dimly, because it's only one ray instead of all of them coming together, very dimly hitting multiple places. And not only does that mean light is being shown on the screen at different places representing the same object, but we're also confused by that visually. And so we view it as blurry. We just sort of mesh it all together. So that perception idea is coming back. So what do I have to do to get a clear image? Well, I better move my screen so it's here at this location, because that's where the image will converge. Let's shift back to my optical bench. So again, no change. But as I slide my screen further away, I don't know if you can see that, but I see very beautifully that this image gets larger and starts to come in focus. Larger and starts to come in focus. So our image has been maintained, our ray diagramming that we talked about. Okay, I'm gonna hold off. I'm gonna turn back to the front because we have to talk about what happens if I change this even more. And then we're gonna, actually I'm gonna change my game plan for today. If there are any, oh goodness, I'm running out of battery. Are there any questions moving into this new room? I forgot to plug my computer in. Any questions about this image formation in a convex lens, real images, and I'm going to introduce the other kind in just a sec, or changing locations to change the image? Okay. Either I've put you all to sleep, which has to be impossible with my high shrieky voice, or we're doing good. Okay. So I'm going to erase this, and I'm going to introduce what happens if we put the object really close to the lens. So here's my optical axis. Put my lens up there. And then I'm going to give myself a focal point. So it's one on each side. All right. We've already done ray diagramming on this side of the focal point. What happens if I go inside the focal point? What if I put my object here, really close to the lens? Well, refraction is happening. It's not changing the lens. Nothing changed about the lens shape or the shape of the mediums, the type of mediums. So we actually can do the same thing. We just say that our parallel ray of light is refracted. Ooh, that was ugly. Is refracted through the far focal point, just like it always has been. the second principal ray that we drew, we drew it, I mean, the near focal point was in front. Well, it doesn't change anything. The fact that, I need to draw my lens up a little bit here. The fact that the parallel rays of light up here are still going to refract through that near focal point. So a ray of light that is in line with this near focal point still has to refract out parallel. So it's not going in that direction. This is the ray of light going towards the lens, but it's in line with this near focal point. Just as if parallel rays of light were coming in and going down like that. And we still have that that ray of light that goes to the center of the lens and remains unrefracted. Now we have a problem. What's my problem? These rays of light are never coming together, ever coming together. So there is no place that I can place a screen over here that will allow me to take all the rays of light representing the top of the arrow and get them on a fine print and take a picture of it. None of them. So what happens? Well, if you have ever dug into your grandma's drawer, found that magnifying glass, what did we use those wonderful magnifying glasses for? Well, we see things really big, right? We take that magnifying glass and we would look at a little tiny print. Maybe grandma, I have to admit, I maybe had to do this one for a course. May your eyes never get bad. But we go close to an object and it makes it really big. Well, this is the object I'm reading. Here's my magnifying glass. Here's the object I'm reading. And I hope this works. Let me pull up my Zoom picture so I can see it. So you can focus on that small print. But if I put my magnifying glass, my convex lens, really close to my object, and my eyeball's over here, your eyeball's over here, we see something. I can't put it on a screen, but I can see it and I can interpret it. And what do we notice about it? Well, we notice that it's big. And we also notice that I can read it. It's upright. So whatever I'm seeing is big and upright. Well, how do I get what I am seeing? How can I represent that using these ray diagrams? Well, first of all, let's keep in mind where our eyeball is. Our eyeball is here now, okay? Your camera was here. My eyeball was here. And I see that image over here. If I take these rays of light are hitting my eyeball. Now, my eyeball is a refractory system that is going to converge those rays of light in a refractory way to my retina, okay? So they're going to do that. These 3 rays of light are going to hit my eye and be refracted to the retina in a way that we've already modeled. They would be the same rays of light that would hit my eye as if this was the object. So if instead of looking at this writing through this lens, I instead took away the lens and took away the object and replaced it with this object at this location and this size, my brain can't tell the difference. All the rays of light representing the top of this arrow, this big one, are the same. Now ignore the lens, ignore the everything. There's no refraction happening except in my visual system. Are the same 3 rays of light that are going to hit my eye and get refracted to a real image on my retina same 3 rays of light as the one those are actually coming from this small object through the lens. And this image is what we refer to as a virtual image. It's a virtual image. And it is not real. We're just interpreting it. We're just saying, well, these are the same rays of light that hit my eye if this were my object. So I see that object. My brain sees it because that's the information my brain's been given. It doesn't exist. I can't put a thing here and take a picture of it and keep it forever because it's not real. It's just an interpretation. They're always upright, virtual images. They're always upright. And for a convex lens, they are larger. So the height of the image is greater than the height of the object. This is what we call a magnifying glass. It's making it bigger. Now in physics, magnification, like acceleration, means it can go up or down. We can have magnification to make it smaller. The ratio just is less than 1. But in this case, we're going to use that terminology like you're comfortable with in the sense of it's making it large. So for a convex lens, that's going to be important for us. All right, so a real image is produced in a convex lens when the object is outside the focal point and it changes in shape and size depending on where that object is located. A virtual image is produced by a convex lens when the object is inside the focal point. And it's important to realize that it's not real. It's something that we're interpreting based on the rays of light being properly refracted through our visual system and hitting our retina. Okay, I'm going to erase this because we're going to do the other kind of lens, that concave one we talked about. So, any questions on this idea? And in your show notes, as I like to call them, if I actually remember to do it. So if you don't notice that I posted the PowerPoint pictures that I've showed you last time, please reach out and say, will you post the PowerPoint pictures already? But I will also have an example of this ray diagramming. Okay. So let me check the chat real quick because my image right now is on Zoom. Okay, no, nothing in the chat. All right, so this has all been a discussion of a convex lens. We said that there was another kind of lens, and we called that the concave lens. And we said it looked like 2 little caves bowed in. So for a concave lens, there is my bowed in shaped lens. And what do we see when we shine parallel rays of light through a concave lens? Well, these parallel rays of light coming on the left-hand side, we see that they're spread out. These rays of light here that I'm tracing my fingers through, they're getting further and further and further apart. They're spreading out. They are diverging. So a concave lens, operational, is what we call a diverging lens. It's causing these rays of light to spread out. Now, with the convex lens, we went through that refraction method of zooming in. I'm not going to take the time to do that right now, but it is because of that curvature that the rays of light are bent in an upward direction at the top of the lens and a downward direction at the bottom of the lens. And like a convex lens, the same is true about changing the shape. If I make the curvature sharper, more curvy, in a convex cave lens, I'm going to get more spreading out. I'm going to increase the spreading. And if I make it less curvy, I'm going to decrease the spreading. So let's talk quickly about image formation. And hopefully, maybe you started thinking about image formation and said, well, wait a minute, if those light rays are spreading out, how the heck am I ever going to get an image? Because I'm not able to bring them to a common point. And that would be a good thought, because you can't get an image, a true, real image. So what kind of image are we left with a converging lens? Well, we're left with the only option of a diverging image, or a virtual image. So how do we get our virtual image formation? All right, so we're gonna follow that same sort of process we did with the converging lens. And black didn't work out so good. And this will take us probably to the end of our discussion today. So I'll draw my 3 optical axes. Here are my 3 lenses. They're all identical lenses. In this case, it is a concave lens, right? And there is some vocabulary that we need to understand about a concave lens too. It turns out that we do actually define a focal point of a concave lens. It's not where all the light rays converge, but it is a property of the curvature of the lens and the 2 mediums that the lens is in that lens itself. And how do we get, so I'm going to put the focal point on here. And if I told you it was a property of the curvature of the lens, you might start to realize that that's related to how tight that circle is. So our concave lens has a certain radius that it is a circle to. And we don't really utilize this in our image formation with lenses, but we will when we look at mirrors, because we're going to look at concave and convex mirrors on Monday. And this distance, this focal length, is related to that curvature, like it was with the convex lens, and of course also the mediums. All right, so a concave lens also has a focal point, what we call a focal point. So here's our focal point, and of course that then means there is a focal length, and this is our focal point. All right, so image formation. If we have an object, and I'm just going to use my arrow again, so there's my object. Rays of light representing the top of the arrow, or any space in the arrow, rays of light that come in parallel, we know we're diverged, right? We saw that in our demonstration. Well, they actually are diverged along a line that is in line with the near focal point. So all the rays of light that are parallel are diverged in a line along the near focal point. If we switch directions, just like we did before, that means that rays of light in line with the far focal point. So this is a ray of light in line with the far focal point. It is refracted parallel. And that same ray exists for our ray of light that goes through the center, remains unrefracted. So the question becomes, and this is not in line, so that's not going to end up working very well in my ray diagram. Let me fix that one. I'm going to do this. If I had a meter stick, which is just in the back of the room, this would be much better. Okay, there it is. So, that's refracted out parallel. And if I take all of these rays and I extend them back, and this isn't, I'm gonna get rid of this ray because my lines are just not good. We're just gonna use these two. I get an image where all three rays of light, the top of the arrow would, if I could extend this line back, the top of the arrow would pass through that location. Now, if I have my eyeball over here, this ray, and this ray are the same three rays of light that would hit my eye and be refracted through my optical system, as if I had this small object at this location. So let's just look at that again using our expo marker. So I have to go back to my video so I know it's in focus. Okay, so here's my object and you're my eyeball. And if I put my concave lens in front of it, what do we notice? Well, large object, small image, and it appears as though it even gets a little closer to us. So, well, there's a perception issue there. So depending on where you are, it actually feels further away. It appears further away. Physically, the image is closer to us. So two things have happened. One, we have caused an image that we perceive, but it doesn't really exist. This isn't created by real rays of light. So what type of image is that? That is a virtual image. Virtual. And it's smaller. For a concave lens, a virtual image is produced that is smaller. That was different for the convex lens. So it's smaller. Now, we are running out of time. So I want to pause for a second, but if we were to move our object further away or move our object closer, we would see two things happen. We would see a change in the image location, and we would see a change in the image height. And we're going to start on Monday just recapping that so we can just remind ourselves about image formation. And then, it's not on Monday, on Wednesday. And then we will, in addition, we will look at how lenses are used to correct vision and how vision plays a role in image formation. Now, I made the comment that when we look at an object through our concave lens, it appears as though that object is further away, when the image is actually should be closer. So why do we have an image that's closer? So I apologize, that's what I meant to say. Why do we have an image that's closer, but our perception of that is further away? Why does it look like the marker is so far away? That has to do with perception and not the actual physics. Okay, so here's another mismatch. And the reason that we perceive the object far away is I want you to imagine a person. If I see a person really, really far away, an object really, really far away, we learned that as it refracts through my refractory system, which is a convex system in my eye, forming a real image on my retina, a person far away is going to be really tiny on the retina. It's not going to take up much space because an image height decreases as the object distance increases. So the person is going to be tiny on my retina. So anytime I see a tiny thing on my retina, I have learned that that means the object is far away. Because I know that human is big, but they're so tiny on my retina. So I perceive them, I know them as being far away because they're tiny on my retina. Well, now I put something tiny on my retina. And my brain says tiny on my retina means far away when I have an understanding of the size of the object. So we truly see it as if it is far away when the image is actually not far away. It's actually physically should be produced relatively close. So there's that perception again, mismatching with the formation of the virtual image in reality. Okay, that's it. That's all we got for today. So we're out of time. I'll keep the thing open, of course, in case there's any questions. And on Wednesday, we will just recap image formation in a concave lens to go through this process and help us remind us of those diagramming. Talk about visual correctiveness, nearsighted, farsightedness, and mirrors. And I said Wednesday, I meant Monday. And mirrors. And mirrors goes really quick. We don't do all the details like we did with lenses on mirrors. And maybe start color. Woohoo! It'll be fun. All right, have a great weekend. Be safe. Wear your mask. All that good stuff.